Welcome to the Python Programming Tutorial Series for Climate Mathematics, Theory and Applications, Chapter 11, Python Analysis of Incomplete Climate Data, Part 2. In this video, we will compute spatial averages and visualize their trends. Let's begin with section 11.3. First, let's go ahead and prepare the data. We're going to go ahead and make a temp variable from the GPCPST, and we're just going to copy that data and rename it temp. Then we are going to set up a matrix of zeros and name it area W. We could go ahead and verify that area W has the correct shape with the shape function. We're going to go ahead and force in the latitude range into the first column of that area W. We are also going to go ahead and force the second column of area W to be the long values found in that temp matrix. Next, we're going to convert our degrees to radians. And we do that by first naming our variable. We could go ahead and name it vect A. And we're using the NP cosine on our latitude values found in the temp matrix. We're multiplying that value by pi divided by 180. And then lastly, we are converting all of that to a list. Next, we're going to go ahead and extract those temp values and naming them temp values using the highlighted line on the text. Moving on, we are going to make an area-weighted matrix equal to the cosine of the latitude of the boxes within the data and to 0 for the boxes that are missing data. We're going to enter a nested for loop, seen highlighted on the screen, which is going to go into a Boolean statement to decide if those temp values are truly missing or if they are greater than negative 290. If they satisfy this Boolean statement, we are going to make the area W on index I with index J equal to vect A at index I. Moving on, we are now making an area weight data matrix with the first two columns as lat and long. We are also going to create monthly global averages vectors for 1,645 months. This month span will span from January 1880 to January of 2017. First, we're going to multiply our area W matrix with our temp values matrix, and this is going to be named temp W. Going in and setting that first and second column to the lat and long values that are found in the temp matrix. And then lastly, we are going to divide our temp W summed across the first axis, and we are dividing that matrix by our area W summed across axis equals 0. This will, in fact, give us an area-weighted data matrix. We're going to go ahead and name this area-weighted data matrix AVE, stands for average V. Moving on to figure 11.6, making sure our plot is fully closed from the previous plot we created. Next, we could go ahead and set up a time variable, name it time O, and this will be created from the NP line space between 1880 and 2017 with 1,645 points in between. We're going to go ahead and create the plot. We are plotting time O against that AVEV matrix we created in the block above. We're going to have a line and its color will be black, which is dictated by a K. We're going to set the title, set an X label, and set a Y label on our plot. We're also going to dictate the Y ticks we would like to see on this plot, dictated by the array that is highlighted. We are now going to create a linear regression model and plot the linear regression line. We first need to set up our linear regression instance, and we're going to name it LM. Then we're going to fit our LM with our time O variable with the Y values found in AVE-V. Now, since our linear regression object is fitted, we could go ahead and make predictions from the predict function on the X values dictated by time O. Now we're going to plot that linear regression model, which is going to have the X values time O and the Y values predictions. This will be a blue line with line width 2. We are going to add some text indicating the trend, and the trend will be 0.69 degrees per century. Wrapping that whole block with a PLT show, we do get this area-weighted global average of monthly SAT anomalies, January 1880 to January 2017. Moving on, we could go ahead and print out our GP-CP-ST data and see what a little snapshot of it looks like. We have our lat and long columns as our first two columns, followed by all of our dates and months spanning from January of 1880 all the way to January of 2017. Most of these values do look like they're missing. That is why there is a negative 999.9 in most of these values. We're going to go ahead and extract some specific data from this data set for plotting. We are going to extract all of the lat and long ranges that correspond with Edmonton, Canada. We're going to go ahead and find where the lat and long of the GP-CP-ST data set are equal to 52.5 in latitude and 247.5 in longitude. We're going to go ahead and intersect those indices that we have both of these lat and longs occurring. And then we are going to do a very similar method for San Diego of the United States. San Diego corresponds with latitude equal to 32.5 and longitude equal to 242.5. We could go ahead and print out the intersection of those two arrays that arise from this where function, and we find out that indice 2065 corresponds with Edmonton, Canada, and indice 1776 corresponds with San Diego, USA. Moving on to figure 11.7, we're going to extract the data for a specific box with given lat and long range. Then we are going to plot. We are going to first extract the data that corresponds with Edmonton, Canada, and we're going to go into this GP-CP-ST data set and grab the data. We're going to go ahead and set up a line space that will represent our time, which will span from 1880 to 2017, and will have the same size as our data that was created in the line above. Next, we're going to set up our figure to plot the Edmonton data. Set up that figure using the PLT figure function, and then we're just going to go straight into the plotting function, plotting T against our DEDM data, which is our Edmonton data. This will have the color red, and we are also labeling this line Edmonton, Canada, trend 1.18 degrees C divided by century, with a standard deviation of 3.01 degrees C. We could go ahead and set some plot labels, set our title equal to monthly temperature anomalies history of Edmonton, Canada and San Diego, USA. We're going to go ahead and set our Y label, set our X label, set our Y limits and rotate those Y ticks so they are in a vertical fashion. Next, we're going to plot a linear regression line that corresponds with our Edmonton data. We're going to open that linear regression object. We're going to fit it using our time variable, which is t, with the y values that is dictated by our Edmonton data, which is DEDM. We're going to make some predictions from our LM object that is now fitted, and we are making predictions on our time variable, which is t. And then lastly, to actually plot that linear regression line, we are going to be plotting our t against the predictions, and this will have the color red. Now we're going to go ahead and create and grab that San Diego data using its indice that we located up above, 1,776. We're going to go ahead and call this data San, and we are going to locate the San Diego data from years 1880 to 2017, seen in the highlighted text. Next, setting up our t variable in a similar fashion. It will span from 1880 to 2017 and have the same length as our dSan data. Next, we're going to go into plotting the San Diego data using that PLT plot function. We are plotting t against dSan in the color blue with the label San Diego, USA trend 0.76 degrees C divided by century with a standard deviation of 0.87 degrees C. In a very similar fashion, we're going to set up a linear regression object. We are going to fit it to the San Diego data, make predictions off of the time variable on our San Diego linear regression line, and then we are plotting those predictions by our time variable. We do want a legend to pop out, so we do need the PLT legend function in there to make sure that our labels get on our plot. Wrapping that whole thing with a PLT show, we do get this monthly temperature anomalies history of Edmonton, Canada and San Diego, USA. We could see that the red line that is seen on the screen is Edmonton, Canada. This trend line has a slope of 1.18 degrees C per century with a standard deviation of 3.01 degrees C. Our San Diego data is in the blue and has the blue trend line, which has a slope of 0.76 and a standard deviation of 0.87. We could go ahead and print out the linear model coefficients and standard deviations of each data set. We're going to just grab those coefficients using the .coef underscore method on each linear regression object. And to compute the standard deviation, we are using the NumPy standard deviation function that is highlighted on the screen on each of the data sets. We do verify that we do have all the correct linear model coefficients as well as standard deviations. Moving on, we are going to go ahead and download the Ncei spatial average time series of monthly data. You can grab this data set from the highlighted URL. Once you have located that, we could go ahead and run a read table function and name this data AVE Ncei, which stands for the average Ncei data. This data set does not have a header, but we are using white spaces as our delimiter. We could print out the shape as well as grabbing the values that are found in that table that we just extracted. We are going to name these values AV Ncei. We could go ahead and print out the shape of that, wrapping the shape with a print function. We could create a time variable that spans the needed years, which will be the line space between the first index of that AVE Ncei dataset and the last index in the AVE Ncei. And we are just going to match the length of that dataset that we are using. This variable will be named time O. Next, we're going to create a matrix of 136 years, which will be our data matrix. We have row equaling year from 1880 to 2016, and our columns will match month 1 through 12. Setting up a AVE variable, which we are going to access all rows in that AVE Ncei dataset, accessing the third column, which is dictated by the second indice. We're going to go ahead and name a M year, which will be the length of AVE divided by 12, and an N year, which will be the integer from the floor function operating on M year. Next, we are going into creating an N-mon variable, which will be our N year variable times 12. Now we could go ahead and reshape the monthly averages into a matrix. We're going to name this matrix AVE-M, and it will be the AVE matrix from 0 to N-mon reshaped into the 137 rows by 12 columns matrix. We could go ahead and compute the annual averages. First, we need to set up a ANNV variable, which will be an array of zeros that has size of 137. Then we're going to enter a for loop spanning from 0 to N year, and we're going to set each value in our ANNV array equal to the mean of that row on all columns in our AVEM data matrix. Now we could go ahead and put the monthly averages and annual average in a matrix. We're going to go ahead and wrap our AVEM data matrix in a pandas data frame function and name this data frame AVEMY. We are going to add a column that indicates the averages. We're going to name this column average, and it is the values that we created when we were filling the ANNV array. When we run this block of code, we do get the AVE Ncei shape to pop up. Taking a look at our AVE MY data, we do see that we have 137 rows by 13 columns, where our last column is the averages of each row. Moving on to figure 11.8, we're going to plot 12 panels on the same figure. This will show us the trend for each month. Setting up that figure function, we have a PLT figure with a specified fig size, creating our time year variable, which is dictated by the highlighted text. Then we need to go ahead and locate and plot each month on separate panels. We're going to enter a for loop that ranges from 0 to 12. We will have 4 rows and 3 columns in our figure, and each indice will be represented by that last parameter, which is going to be I plus 1. We're going to go ahead and plot the time year by the AVEMY location on all rows, but in the ith column. This data will be colored in black. We're going to go ahead and set the title of each small plot within our figure. We're going to rotate those ticks to the vertical fashion, set our Y label, and set our X label all within this for loop. In addition to plotting the actual data in black, we are also going to plot the linear regression line that corresponds with each of these months. Opening our linear regression object, fitting our linear regression object to our time variable with the y values dictated by AVE and y, all rows in the ith column. Then we're going to make predictions from that fitted linear regression line and go ahead and plot that time variable by our predictions. Adding a little bit of text to our plots, we are going to add the coefficient of each linear regression object that is created from each subset of data, and we are just going to add trend degree C per century equals this coefficient that we are grabbing from each linear regression object. We're going to go ahead and set that y limit, set the x ticks and the y ticks as well. With that, that concludes our for loop. So once this for loop is ran, we will get 12 separate plots that represent each month in our data that we are looking at. We do need to wrap our whole block with a PLT tight layout function to ensure that we don't have any overlapping values. As well as wrapping that all with a PLT show, we do get a 12 panel, same figure plot representing the months of each AVE-MY data. We have month 1 through month 12, all with their linear regression coefficients printed on each plot in red, as well as their linear regression line superimposed over the data. Moving on, we are going to create the difference data, and then we're going to plot the difference data. We create the difference data by using the NumPy package, accessing the subtract function, and we are subtracting our AVE V matrix from our AVE Ncei data on these indices from each other. This will create the difference data. Then we're going to go ahead and go into figure 11.9, where we're going to compute the annual average and then plot the annual mean global average temperature. We're going to go ahead and rename AVEM as our reshaped version of AVEV from indices 0 to 1644, and we are reshaping this in the -1 by 12 shape. This shape will give us a size 137 by 12. Then we are going to go ahead and average over those columns. We're going to name this average ANNV, and we are just taking the mean of that AVEM on our axis 1. Then going into setting up our time variable to get ready for plotting, we're going to go ahead and use that NPArrange function from 1880 to 2017. We're going to make sure that plot is closed from the plot above, and then we are actually going to use a step function in this case. We're going to step our time by our ANNV array that we created above. This will have a step of black, so our line that we see will be black. We could go ahead and set the title, the X label and Y label, seen highlighted on the screen. And we are also going to add our linear regression line, setting up that linear regression object, fitting that linear regression object with our time year and our averages over our 12 months. And then we are making predictions, trying to predict what our linear regression object would predict for our time sequence. We are then going to plot our time year by our predictions, and this will have the color purple. We are going to go ahead and add some text on the plot, just some informative trend lines and our baseline. We're going to go ahead and plot that baseline by plotting time year on an array of zeros. This will be a red line. Wrapping that whole block with a PLT show, we do get this area-weighted global average of annual SAT anomalies from 1880 to 2016. We can see we have a step function rather than a normal plotting line. This step function is frequently used with years in climate science, and it just allows us to understand that each of these measurements is for a specific year, not a specific day. We can go ahead and move on to comparing this with the Noaa Global Temp annual time series data. We will notice that there are some small differences when going through this data set. We're going to go ahead and name our Noaa Global Temp data AVE NN Ncei. We're going to read in that table from the Climate Mathematics website, which is highlighted on the screen. This data does not have a header and it will have white spaces as its delimiter. We could go ahead and print out that shape of this data and go ahead and extract the values of it. We are going to make another difference data, subtracting our A and NV from the data we just imported. We could go ahead and find the value range, minimum and maximum values in our diff2 array, which is highlighted on the screen. We're going to go ahead and print those out using the highlighted text on the screen, and we do get the minimum and the maximum values printed out. Moving on to figure 11.10, we are going to polynomial fit our global average annual means. We are following the polynomial fitting from the NumPy polyfit function, which is not orthogonally plotted. We know that orthogonal polynomial fitting is usually better, as we saw in the R code implementation of this same tutorial series. We're going to go ahead and use this polyfit function on our time year with our ANNV data using 9 slope coefficients. We are also going to fit a 20th polynomial using that same time year and ANNV. Making sure that plot is closed with that PLT close, we're going to go ahead and use our step function to plot our actual data. Add our title, X label, and Y label to our plot. And now we are going to go ahead and plot our first polynomial fit. We are accessing that PLT plot function, and we are using the time year as our X, and we are going to go ahead and use a NumPy polyval on our 9th order polynomial fit with the second parameter equal to time year. This will give us out the predictions that this 9th order polynomial fit will approximate for our time year sequence. Then we're going to do the same thing with our 20th order polynomial fit. We do want to print out a legend, and we could go ahead and dictate the location to the upper left of this plot. Wrapping that with a PLT show, we do get this polynomial fitting to the global average annual means. This concludes Chapter 11, Part 2. Join us next time for Chapter 11, Part 3, where we will examine spatial characteristics.